Yeah, I'm Shengyao from Sarah, Australia. This is joint work with Honglei from Google and Bevan, Guido from the University of Queensland. The title is a Setwise approach for effective and highly efficient zero-shot ranking with LLMs. So first, let me introduce our research background. In this paper, we studied the problem of prompting LLM to rank document in zero-shot manner. When I say zero-shot, I mean you take any open source LLM, you just prompt engineering them to rank documents without any further fine-tuning. So in literature, there are three types of methods have been merged. They are pointwise, listwise, and pairwise. So let me quickly overview these methods. For pointwise methods, so in the prompt, you give the document or passage you want to rank and the user query, a pair of texts, and then you just prompt LLM to say does this passage answer the query, yes or no? And then in the output side of LLM, you can check the logits, output layer logits of yes or no tokens, or you can just use these tokens and this probability of generating yes token to rank this document. So this probability we often refers to logits. For listwise method, instead in the prompt you give a list of documents, so many documents or passages, and the instruction is to ask LLM to generate these passage labels in an auto-regressive manner, and hopefully the generated labels are relevant in the order by the order of their relevancy to the user query. For the pairwise, it's like kind of special case of listwise. So instead of list of passages in the pairwise, you just give two passages, and the instruction is which passage is more relevant to the document. And then you can let the LLM generate the actual label, or you can check out the logits, which label is higher, then the higher one is more relevant one. But because there are only two documents, if you want to rank 100 documents, the naive way is you compute all the combination of these pairs documents in your 100 candidate documents, and then you inference them all with LLMs. You use the voting method to check which documents wins the most in these pairwise comparisons, and then you rank based on this number of wins. So all the literature have shown this method to be effective. However, different studies use different backbone LLMs or with different sizes and different experimental setup, so making it very hard to fail compare across different methods. In addition, another fact that is overlooked by this literature is their efficiency. As you can see, different methods have very different mechanism of inference. So pointwise can use logits, and they can use batch inference with your GPU. So probably it's more efficient. You use GPU resource more efficiently. Listwise instead can only rely on this autoregressive generation, so probably it's not that efficient. So the first contribution of our paper is we try to constrain the evaluation setting by using the same LLM, same data sets, and the same initial ranking. Basically, we take BM25 and ask all the method to rank top 100 documents. So in this very constrained method, we hope we can fairly compare all the different methods. And of course, in addition to the effectiveness, we also care about the efficiency of different methods. So we check the query latency, number of LLM calls you need during the inference, and the total prompt tokens in the prompt as the metrics for efficiency. So let's first have a look at the effectiveness. Here I show different methods with flan T5 from large to XXL. I think it's from less than 1B to 11B. And here I show the result on TrackDL dataset. We also have result on beer dataset. The story is a little bit different for some of the subset of beer dataset, but for simplicity, I just show DL here. I encourage you to read the paper for more details on beer. So as you can see, the pointwise method seems not impacted by the model size a lot, right? Increase your model size doesn't help with the effectiveness. Listwise method instead work well only with the large model size. pairwise seems like pretty robust to different model size, and larger model indeed give you further improvements in terms of the effectiveness. We also, evaluate these LLMs on popular decoder-only open source model and closed source ChatGPT 3.5. I exclude pointwise here because, like, if ChatGPT is a closed source, you don't get the logits really of the model output layer. So as you can see, the small models are like, pairwise and listwise are very bad with small size models, but they works like better with model size increases. And ChatGPT works the best, which is kind of expected. Okay, for the efficiency result, the story is kind of different. Here I show the query latency of different methods, with Flantify, different model size, and interesting here, the y-axis here is the latency in seconds and in log scale. So as you can see, the listwise and pairwise are super slow than that of pointwise. This is because the listwise needs this autoregressive next token prediction, one next token prediction meaning one more LLM inference, and the pairwise instead needs to compare all the pairs of combinations, and meaning there are lots of LLM inferences. And same trend for number of cores, LLM cores, and number of tokens in the prompt. And if you use like ChatGPT, API-based method, this equals money, right? You spend a lot of money to rank these documents. Okay, so the obvious question now is how to improve the efficiency of listwise and pairwise methods. Okay, so here the original pairwise paper actually proposed to use classic sorting algorithms to speed up this pairwise inference. So here I show you a toy example of how they use heapwise methods, heapwise sorting to speed up pairwise methods. So actually, let's do the practice together of this classic sorting algorithm. So on the left-hand side, I show you the initial ranking list, and so these nodes are represent documents you want to re-rank, and the number in the nodes represent their relevance level to the user query. Bigger is more relevant. So the first step of this sorting algorithm is you build up this binary max heap tree, which the parent node is the number in the parent node is bigger than its child nodes, and building this tree costs you n log n pairwise comparisons, and then so at this point, the root node is actually the best documents, and then you just pick out the root node, move one leaf node to the root, and then the step 2 is heapify this tree again. So basically, let's do this together. So the first thing is you compare the root node, the child node of the root nodes, and so pick these two nodes into pairwise prompt. Ask LLM which one is bigger, which one is more relevant, one LLM core, and then 9 is bigger, so you compare your root node with this your left child node, one more LLM core, and then you find the child is bigger, so you swap the two, and then you do this again for the subtree that you have changed, one more LLM core. And then you do this again, one LLM core, you swap, you move next, plus one LLM core, and then compare again, one LLM core, and then you swap. So at this point, you heapify the whole tree, right? Because you 6 LLM core, and the next thing you just you find the second best node document, you move it out, put another one, and do this heapify again. So each time is log n complexity to heapify the tree. But compared to you compare all the pairs, which I think is quadratic, this is much more efficient. And you can use bubble sort as well. So you do bubbling sort from the bottom of the list to the top. So I just skip here. So as the result, as you can see, use this bubble sort or heap sort can significantly improve the efficiency of pairwise methods. However, if you look at the XSL, the most efficient heap sort still costs you like more than 50 seconds to rank 100 documents. So it's still very slow. So can we do better? So this is the contribution number 2 of our paper. We propose a new prompting method to rank the documents. We call this setwise prompting. So in our setwise prompt, instead of putting 2 documents to compare in the prompt, we put a set of documents, so similar to listwise, many documents in the prompt. And then we just ask the LLM to select which one is the most relevant among this set of documents. Then similar as pairwise, you can check the logis, which one is the highest probability, or you just let the LLM to generate. Meaning like you can fairly easy to use a closed sourced method to inference as well. Another interesting property of our method is we can actually rank the documents in all the documents in the prompt as well, just like listwise. This is done by rank the probability of passage labels according to tautologis. But of course, the constraint here is you have to have access to the model output layer. But it turns out this can speed up listwise method as well, which I will talk later in more details. So let's first have a look how this kind of prompt can improve pairwise methods, the efficiency of pairwise method. Instead of binary max heap tree, now I actually building a multi-node max heap tree. It's similar to binary, but it's just more child node, and the root node is always the biggest. And then you want to heapify this tree. I skipped the step 1, so let's directly go to how you heapify the tree. So because our setwise prompt allows you to compare multiple documents, basically just put all the child node plus root node into the setwise prompt, one LLM core, and let them tell you which one is the most relevant. You swap that with the child node, and then you move next, another LLM core, you swap. And then at this point, you finish the heapify with only 2 LLM core, right? Before was 6. So this can, obviously reduce. And then you just do this, swap, rank, pick out the best one, put one leaf node there, and do this again. Same for the bubble sort. You can, speed up this bubbling as well. So for the efficiency result, like the bubble sort algorithm here, it can significantly improve by more than 100%. And for the heap sort, you can, another considerable improvement for efficiency. In terms of effectiveness, actually, we find either pairwise or combination pairs comparison, or you use pairwise, setwise with all, sorting algorithm. They actually perform very similar. So no effective loss here. But that's for the flantify. We actually find for the other decoder-only method, like for the small size decoding method, our setwise actually much better than listwise and pairwise. So that's kind of good. As I mentioned, our method also can improve the efficiency of listwise. This is because listwise need one token autoregressive generation, but our method can only do one inference, then you rank all the list. So you avoid this multiple inference. In terms of effectiveness, we find that's the where is the efficiency? Hang on, yeah. So this is the efficiency result. Our listwise log is used with using our setwise prompt can significantly improve the listwise generation. For the effectiveness, it's actually even much better. So it's very good. To conclude our work, we have contribution 1, systematic evaluation of existing method, and also we look at the efficiency of the method. And contribution 2, we propose new setwise prompting method. which can further improve this existing pairwise or listwise method. And we also made our code available here. And I tried to make our code easily to use, so you can simply pipe install our library, and then you import setwise, listwise, pointwise, etc. And then you can rank your own documents with few lines of code. And that's it. Thank you.